Okay, so today we will be talking about relativistic relativistic quantum physics or relativistic quantum mechanics. Well, physics rules work, no problem. Did I just write the spelling of physics wrong? How can I? If I don't know the spelling of physics, that will be a shame to me. Okay, so before let's do a little overview. I want to show a difference between three equations. The Schrodinger equation, the main equation which governs the quantum mechanics world. Second, Klein-Golden equation. I will make a video on it soon enough, but and then Dirac equation. So okay, I want to show. I have made video on Schrodinger equation, but I have not made a video on Dirac and Klein-Golden equation, which I will soon make, soon to come. All right, soon to arrive. Let's be fancy. They will soon. I will make a video on them. Okay, so Schrodinger equation. I have told you the how to draw Schrodinger equation. What is Schrodinger equation? What is the how it works, what it does, and we have talked about it in other videos, so I won't focus on it that much. But here I want to show the difference between Schrodinger equation, Klein-Golden, and Dirac equation. That Schrodinger equation is a non-relativistic equation, whereas Klein-Golden and Dirac equation are relativistic, means that they both will have different observations with respect to speed of light, with the speed that object or the observer is moving at. So we have Schrodinger equation. We have talked about this non-relativistic. It's applicable to most practical QM problems, non-fashionably Newtonian, philosophically unsatisfying. Yeah, it's but the equation. There's a reason it's known as the best equation or the governing equation of the quantum mechanics because of its um, difficulty plus its the probability it gives. So our topic today is I just wanted to give a overlap or the main overview. So Klein-Golden is again quantum physics. All these are for quantum physics, and Klein-Golden beautifully unite of space and time. It unites space, time, energy, and momentum. This one antimatter. Dirac equation is mostly for antimatter. Klein-Golden is for field, and this for the particle. But Klein-Golden doesn't have a spin, unleashes the horror of the spinners onto the world. Yeah, it's whatever, so on. Your life, okay. So, then the main topic for today is mass shell. Okay, mass shell. So first of all, what is mass shell? Mass shell is a condition where energy, momentum, mass, and what was the other one? Yeah, something like this come together satisfy the uh, satisfies the conditions that satisfies its existence. If that principle or that object doesn't uh, fulfill this condition, fulfill, which is the condition is what? That number one has mass, number two has momentum, number three has what again? It also has energy and so on. It's known as four momentum space. So if I try to like visualize the mass shell, I will visualize it like this. Wait, I not let me just make it 2 dimension for now. This is the mass. Okay, I'll tell you what's the difference between these two. Okay, before that, we will see how we can combine momentum and energy for the mass shell, because these are two main things. We know that momentum equal m. Momentum is energy is mc square, and momentum is I h bar this. But I don't think so we will be looking at this for now. Let's leave it for here. But the main thing I want to show is P and E over C together combines to give our momentum and energy relationship for a mass shell, which is P. When I say P, this arrow means it's showing direction. We have talked about vector quantity. No, we didn't means we know that vector quantities have arrows behind on top of them, like velocity. It has an arrow on top. It means it has a certain direction. So if I open this bracket, I would get for E over C it would remain the same, but this over here would turn into P. Wait, let me change color again. Not let's not use the same color. We will talk about px, py, and pz. You all know what py, x, y, and z, and these are the coordinates. These are what the coordinates are. Okay, so now this is done. This is how we describe it. But now we will talk about the square. We will take it square. That's how it works. We take the square magnitude. Square magnitude. Square magnitude. What is square magnitude? It's just taking the square of all of these, which is E over C square, and then px square. Px square. Was it plus? Yeah, it was plus. Sorry, I didn't mean to do that. It's plus px py square plus pz square. Okay, here if I one more thing, when we are looking at the signs of these quantities, mostly we look at the what was that, Minkowski, something like that, principle. And there's a principle which is that if one of the quantities is negative, the other one has to be positive to show the difference. So if I'm saying p or momentum as positive, I will be taking energy as negative. It will be a rule, or vice versa, but they should not have the same sign. Okay, so this can be written as E equal, or wait, was it P? This is a dot product of P dot P E this and E over C square. No, this. Yeah, it's a dot product of, this is what the dot product of it is. Okay, so when we then expand, no, not expand, now let's take this example. Now we will be taking this example back again. Now we will integrate it. Wait, let me just cut it over here. So what happened? Okay, so what I will be doing is I will combine it. Now over here, let's bring our equation mc square dot p squared, this direction. It's saying this p with this square means the same as what we did over here. Wait, is over here. Okay, so imagine this area as a space where a particle with in a certain space with momentum and energy, and it's under some kind of effect. And so if I show this, no wait, it should be like this. So what I'm saying here is that the more quantities or the more values we have in this equation, what will happen is that it will affect the curvature, or in my word I'll say it's a curvature. Okay, what will happen is that this over here means more mass, more. This over here means less mass, and this over here, which is at the ground, means zero mass. So it depends on our values of this equation. Zero mass, which is that a particle in a space with momentum and energy. When I say energy or mass, I'm talking about rest mass. Rest mass means its mass when it is observed, when it's not moving. Because we know that something which moves, or wait, it comes to another topic: mass, rest mass, and mass. There's a difference between these two. It's good to know about the difference, so we'll talk about it. Rest mass is when the mass is not in motion, or the mass is observed while stationary. Stationary means while it's at a point, it's not moving. Okay, this is one example. This is an example for rest mass. The example for the definition of mass is same thing, vice versa. The mass is observed when the particle is moving or the observer is moving. Let me show you the equation. If I write the equation for the one which is moving, it will be mass equal mass at rest. This point's rest. This over here shows mass rest divided by gamma, and then gamma is what, since we're talking about relativistic, it's a relativistic video, so we can talk about gamma. 1 minus v over c squared over this is what gamma is. What is gamma again? Gamma is a time dilation factor, showing that if something is moving at a certain speed, it will be affected because of the speed of because of its speed going near the speed of light, and that for the time for him will slow down. That's the fastest I can say. So what else? Yeah, let's get back to our topic. One more thing over here. When we say mass shell, we are not talking about only positive. Here then we have something known as mass shell with positive and negative. So yeah, mass shell can be positive and negative. Amazing, right? This is positive mc squared plus, for the plus, wait, minus p squared and this, oh wait, let me change color. This is minus square root of mc square under root minus b square. This is the difference for the shells. And in short, what I'm trying to say here is, in short, you might have also guessed, in short, we are talking about the particle and antiparticle. Antiparticle. Yes, because if a particle has positive charge and it has a certain momentum with mass, there will be a it's a twin which will have a negative charge of uh, a certain mass and energy. And in my guess, what I think is that they anti-particle and particle should sorry should have same mass and energy and momentum. This is my observation, or this is what I think if I look at this equation. So then what else? 16-minute video. Okay, was I missing something here? I think I talked about everything I know. What else can we say? Yeah, so again, one more thing. Let me choose a different color. Black will work. Over here, this is a 2D. It's a 2D visualization of mass shell. They can be 3D and 4D, because 4D, if we have, let's suppose if we have 4D will be having 4D or 4 momentum 4 momentum term will have mass, energy, momentum with plus time. But then it would be a massive, it would be a very huge, like it would be moving, it would have multiple, like over here like this, this symmetries, then over here, down here again, one more symmetries, 4D. And yeah, that's it. I try to make it as simple as possible. Thank you.